Good morning. This is the last part of number theory that we are supposed to work, and I would say that is the pinnacle of number theory. So modular arithmetic. Uh, we want to see what is this topic about, okay? Um, so let me start with the definition first, then of course I will describe what do I mean. So definition. Let m be a natural number greater than 1. And let a and b be integers. We say that a is congruent to b modulo m, and write a, you just use this symbol, and I think in your book they are using this, or I use the short version of this. If a minus b is a number which is divisible by m. Yes? So this is just a definition, very, very simple thing. So I'm just trying, I will not use this notation. It's unnecessarily long, but this is probably the most standard notation. So I will use this. So whenever you see this symbol, what does it mean? Whenever you see this symbol A, you read it in this way. A is congruent to B modulo M. It's as simple as this. First of all, you have to have some rules. M is a natural number greater than 1, but a and b are integers. So when you see this symbol, it means that this is equivalent to saying this. Yes, that's it. You might say that why we make trouble for ourselves, because we already studied this divisibility, so why we are inventing another notation for that? You will see that this will be much more stronger, or at least more straightforward to understand things in number theory. So for example, let me just give you some examples. So example, for example, I can write 15 is congruent to minus, let me write first simple. So 1 modulo 2. Yes? This is a true statement. If you want to see if this is true or false, you have to translate this into the language that you already know, that is divisibility. If this turns out to be true, you would say this is true. If this turns out to be false, that is also false. That's just my definition. So is it true here or false? So you would say that if this is going to be true, this means that the number on the left minus the number on the right should be divisible by the number on this on top here, which in this case is 2. Yes? So is this true or false? True, because 15 minus 1 is 14. 14 is divisible by 2. So this is true. This means that this is also true. But that's nothing. I'm just introducing another way of writing the same thing. Okay, so this is true since you can write this. 15 is equivalent somehow, is congruent to 1 modulo 2. The reason is that this is correct. But for example, 15 congruent to 1 modulo 4. Is it true or false? This is false, yes? Because is false. Since if you write the number on the left minus the number on the right, it is not divisible by the number on the top, since this is false. Okay, but of course you have to train a little bit yourself to get used to this new symbol and notation. Okay, so for example, what do you think about this? 12 is congruent to 40 modulo 7. True or false? I don't know. I think it is true, isn't it? So is since what? The number on the left minus the number on the right is minus 28. And minus 28 is definitely divisible by 7. So that is also true. Yes? So I want you to think in this way. If you work in modulo 7, 12 and 40 are the same numbers. This is a good way to think about it. Of course, 12 and 40 are not the same numbers, we know that. But if you don't care about other things, you just decide to work in modulo 7, there is no difference between 12 and 40. Yes, if you work, of course, in modulo 7. But if I work in modulo, I don't know. So do you think they are also the same modulo 2? Yes or no? Are these two numbers are also the same if I decide to work in modulo 2? The answer is yes, because the difference is minus 28. Minus 28 is divisible by 2. Are they equivalent if I decide to work in modulo 4? The answer is again yes. So that's it. So it means that how many names you can attach to a number if you decide to work in a particular module? Infinitely many, yes? So you can just... So for example, can you give me another number, another name for 12 if I want to decide in modulo 7? For example, do you agree that another name could be negative 2? Do you agree with this one as well? Because the number on the left minus the number on the right is divisible by 7. True or false? It is 14. So it means that if you decide to work in this module, in principle, there is no difference between 40, 12, or minus 2. So you can just cook up infinitely many names for the same number. It is not very surprising. Even the fractions that we were working in real numbers, 1 over 2 is the same name for 2 over 4. It is equal to 3 over 6. So that is also sometimes we already are familiar with that. So we have different representations for the same number, for example. Okay. What about this one? So 42 modulo is congruent to 0 modulo 6. Do you agree with this one as well? Yeah, so it is very good, by the way. 42 is relatively big number, but if you decide to work in the module 6, it is just 0. Just it's easier to work with 0, and that is the power of modular arithmetic. So it doesn't matter how the big number is. I can just ignore them and work with fairly simple numbers. Okay. So for example, let me translate this. By the way, why do you think I excluded 1 from the m? Because there is nothing interesting going on, yes? If I choose m to be 1, then what happens? Yes, every number is congruent to every number in that module. So that is not a very good idea, because if m is 1, this is always guaranteed, regardless of my choices for a and b. Because whatever a and b are, it is divisible by 1. So this is why it is better to exclude 1 from m, yes? Okay, so that is the reason that we say that the module should be greater than 1. Okay, one thing is, what happens if a is congruent to 0 modulo m? That is also good to know. So I would say that a number a is congruent to 0 modulo m if and only if what happens if and only if a minus 0 is divisible by m. But a minus 0 is nothing except a. This means m divides a. So that is a good remark. I will use it later, okay? A is divisible by m if and only if, this IFF means if and only if, you can show that a is congruent to 0 modulo m. Yes? Okay. So there is one important theorem that I want you to understand here. So let me just write a theorem here. So working with congruency is easier for our brain than working here. For example, this is very close to equality. So whatever you know from equality is more or less valid when you are using this symbol. For example, in equality, if a number a is equal to b, if you want to, you can conclude that b is also equal to a. But this is not the case for this symbol. If a divides b, there is no guarantee that b also divides a. So this is not symmetric. You see a symmetry here. Yes? So this means that this is harder for our brain to work with this symbol rather than this symbol, because this symbol will mainly enjoy all the properties of equalities that you expect. Okay, let me just list them here. For example, I would say let a, b, c, and d be integers, and let m be a natural number greater than, yes? A, B, C, and D. Yes, thank you. Okay, then, of course, some of them are very clear. Every number a is congruent to itself. It is exactly similar to saying that every number is equal to itself. Of course, every number is also congruent to itself in any modulo that you like. Number 2, if A is congruent to B modulo M, if you want to, you can conclude that it is symmetric. So B is also congruent to A modulo M. Part C, if A is congruent to B and, this means and, yes? B is congruent to C. So this, I hope that you can immediately anticipate what is going to happen if you just compare it with equality. If a number A is equal to number B itself is equal to number C, what can you conclude if you want to? You can conclude that A is also equal to C. So that is also true in congruency. Yes, if A is congruent to B, B itself is congruent to C, but be careful, I am keeping the modules the same. Then, if you want to, you can conclude that A is congruent to C in the same module. So number 4. So assume that you have a congruency, and then let us say if you want to, you can add the constant number C to both sides. Still it is true. So it becomes A plus C is still congruent to B plus C modulo M. You see that everything that I am writing down as if I am writing it for equalities, yes? If I know two numbers are equal, you know that I can add the same number to both sides, but still equality is again valid. I can subtract them, yes? So I can also subtract here if I want to. I can also multiply, yes? Number 5, so A is congruent to B modulo M, then you can conclude that C times A is also congruent to C times B, the same module. You see, you really don't need to memorize anything because they are exactly more or less carbon copy of the properties of equality sign. So working with them is much easier than this asymmetric relation, yes? So number 6, let me just expand this list a little bit. Number 6, if I have A congruent to B in modulo M and C is also congruent to, say, D, the same module. Do you remember, if I have this, what can I write, for example? If I have A equals to B and I tell you that C is also equal to D, you can conclude something, yes? You can say that A plus C is also equal to B plus D. If you want, you can conclude that A minus C is equal to B minus D if you want. Or even if you want, you can multiply, yes, side by side and conclude it. But of course, in equality, you can also divide. If C and D are non-zero, you can conclude that A over C is equal to B over D. But you shouldn't expect that in number theory, because in general, when you divide, you are facing fractions. But this symbol is only defined where the left-hand side and the right-hand sides are integers. So you shouldn't expect that you can also divide, but everything else you should be able to conclude. So you can conclude here that A plus or minus C is congruent to B plus or minus D modulo M. And number 7, let me write the multiplication. So what happens? A is congruent to B modulo M. C is congruent to D modulo M. If you want to, you can conclude that A times C is also congruent to B times D modulo M. And then finally number 8, if A is congruent to B modulo M and N is a natural number, okay, then you can also raise to the same power of n both sides. So you can conclude that A to the nth is congruent to B to the nth in the same module. So the good news is that working with this new relationship between integers is much simpler for us than the other relation, because they are very, very similar to the their counterparts in equality relation. Is that clear? Okay, but let me just try to motivate you about some of them, why they are true. Because whenever I write a theorem in mathematics, what you expect is proof coming after that, yes? So let me just try to, not all of them, but the hard ones. Okay, so let us try to discuss together. For example, let us understand this. Do you agree that A is congruent to A? Why is that? Because whenever you want to check if this is true or false, what you need to do? You need to write the number on the left minus the number on the right, and then check if this difference is divisible by the module. In this case it is, yes? So what happens? Yes?
Is it not possible to divide on both sides?
No. That I just told you that, yes? Because if you divide, in general, you get fractions involved. And division, this symbol only makes sense if you have integers, not fractions. So you shouldn't expect that this also be true, even though that is true for equality, but not here. Okay, A minus A is 0, regardless of the value of A. But 0 is always divisible by m, yes, according to what we had before. Yes, m is a number larger than 1 and it is integer. 0 is divisible by an integer. So this is the reason this is true. Why this is true? If you tell me that A is congruent to B, I conclude that A minus B is divisible by m. But I hope that you agree with me based on your experience so far. If A minus B is divisible by m, B minus A is the same number with the opposite sign that will also be divisible by m. So if you tell me, I am allowed to conclude this. Okay, for the first one, let us prove this. Why this is true? So you tell me that A is congruent to B. You are also telling me that B is congruent to C. The meaning of this sentence is just the definition. This means that if I write the number on the left minus the number on the right, this becomes a number which is divisible by m. And when you tell me this, I am allowed to conclude the same thing for this. It means that the number on the left minus the number on the right is divisible by m. Yes? So what is your goal? If you go to a scratch work, so what is my goal? My goal is to show that A is also congruent to C in the same module, yes? So what does it mean? It means that I have to convince myself that A minus C is also divisible by m. If I can show this, I am done. Agree? Because my goal is to show that A is congruent to C modulo m. What is the meaning? It means the number on the left minus the number on the right should be divisible by m. So this is my question mark. If I can convince myself of the truth of this statement, then I am done. But this is easy. Why? Because now you have enough experience on divisibility. So when you say this is divisible by m, it means that there exists an integer q, so that what happens? A minus B is this number times Q. Yes? And then when you tell me that M divides B minus C, it means there exists possibly another integer Q prime, so that the number on the right is M times Q prime. But now you have your goal, because in the scratch work, you know that you have to have this combination, A minus C. You have A minus B, you have B minus C. Your goal is to have A minus C. So what is the most natural thing to do? Just add them, yes? So I will start adding them side by side. What happens when I add the left-hand side to the left-hand side, which I know it is possible, because I know these things are valid for equality sign. So this B and that B are cancelled. What is left for me is A minus C. And now hopefully you have enough experience. What do you suggest me to do on the right hand side when I add them? because I need a factor of m somewhere, and it is clear that I can factor this m out. So what is left? From here, q is left, plus from there, q prime is left. But am I allowed to call this a q in number theory here? The answer is yes, because q and q primes are integer, and it is clear that if I have two integers, when I add them, it becomes another integer. So what is the result? So what I got is that a minus c is m times a q, but this q belongs to z. So what is the conclusion then? The conclusion is that this number divides this number. Yes? But what is the meaning of this in the language of congruency? This means A is congruent to C modulo M. Yes? So it means that if you give me these two, and I need it in my problem, I can conclude this. That is also true. Okay, so I think these are very simple. You can work them out yourself, and I really recommend you to do this because it will give you the opportunity to practice this new language. But let me solve the harder one. So number 7 is probably the harder one. A is congruent to B. So number 7. So I know that A is congruent to B modulo M. I know that C is also congruent to D modulo M. My goal is to show that A times C is congruent to B times D modulo M. Yes, that is written here. A times C is supposed to, I want to show that this is congruent to B times D in the same module. So be careful. Always these are valid if I am decided to work in the same module. If this is modulo 2, this is modulo 3, we don't know what's going to happen. Yes? Okay, but then I go to a scratch work again. My goal is to talk about A times C and B times D to be congruent. So it means that my goal is to have something like this. This is my goal. Yes? Agree? Okay? This is the goal. If I can show that, I am done. But again, I have to translate this because there is nothing I can do about it. If you ask me what is the meaning of this sentence, this is nothing except that M divides A minus B. If you tell me what is the meaning of this sentence, it means that C minus D is divisible by M. Okay? And then I want to conclude something about ACBD together. Okay? So I have to translate this into equality sign. Because you see, here I have congruency. I translate it into the language of divisibility. Then divisibility is translated in the language of equality, which is we are more familiar with, we are most familiar to it. So what happens is that there exists a q in Z, so that what happens, the number on the right is equal to m times that q. And when you say this, I can conclude more or less the similar result. There exists possibly a different q, which I call it q prime, so that C minus D is mq prime. Yes? But you see that I need to have AC and BD. If I just naively multiply them, it will work, but I think it's not a good idea. Because if I multiply them, remember, I need AC with positive sign, but I need BD with negative sign. So if I just multiply them, it becomes AC minus AD minus BC, which are the terms that I don't need. But the problem is that even the last one that I need turns up with the wrong sign, because if you multiply them it becomes positive BD, but what I need is negative BD. So it might motivate you, this is not a good idea, even though it seems natural to multiply side by side, but might be this is not a good idea. Just do it right now. So then I would say that, okay, let me move B to the other side. So this becomes A is equal to MQ plus B, and then C is MQ prime plus D. And now it is ready to multiply. By the way, I solved that problem. Why? Because if I multiply A and C here, B and D will be multiplied with positive sign. Then I move it to the left, it becomes negative as I need it. Okay? So that's a better way to do it. Okay, so now I multiply them side by side. If you tell me A is equal to that number, and if you tell me C is equal to that number, that I am allowed to conclude that A times C is equal to MQ plus B times MQ prime plus D. This I am allowed to conclude. Based on what? Based on the properties of equality sign. Okay, and then a simple algebra is now involved. So you can conclude that A times C is equal to, I multiply them, M times M becomes M squared, and then I have QQ prime. Yes, and then I have MQ times B, times D. And then I have BMQ prime. And then I have B times D. But in a Scratch work, I have already set up my strategy. I know that I need this combination. Okay, so this will motivate me to move this to the left again, because now it becomes minus BD. And then I know that I need a factor of M. And then the good point is that all of the involving terms actually share an M in common, yeah? So I can pull that out. So let us just do it. I move BD to the left, so it becomes AC minus BD. And from these three terms, I factor one single M out. This becomes MQQ prime, plus the next one becomes Q times D. And the next one becomes B times Q prime. Yes? But the point is that, do you agree with me that this number is an integer now? Because M was a natural number, Q and Q prime are integers, so, and B and D are also integers in the beginning of the problem. So this means that this combination, I can call it Q, and this is important to understand that this is an integer. And now what happens? M times an integer is AC minus BD. So if you want, you can conclude that AC minus BD, because it is an integer multiple of M, it is divisible by that. Yes? And then this can be translated in the language of congruency. How can I translate it? This means this number is congruent to this number in this module. So this becomes AC is congruent to BD modular. Yes? By the way, let me ask you this question to test your understanding. Can you write this in congruency language? If I ask you to write this in the form of congruency, what do you write? That's, by the way, this is important. You should be able to go back and forth very simply. Sometimes it is congruency is given, you have to translate it into the language of divisibility. Sometimes the divisibility is given, you have to write it in the language of congruency. Yes? Minus B, because this can be viewed as a difference as A minus B divisible by M. So this means this is playing the role of the number on the left, congruent. This is playing the role of the number on the right. And then you can write M here. Yes? That's very simple. Any questions? So it took a little bit of time, but of course it was not hard. So now, from now on, you just use them. I don't want you to prove the theorem. This is one of the lessons in the book, so this is why I brought this up. I want you to see the proof, but then you can use it. Yes, please. I told you by C. Okay, then yes, that is possible. Yes. Okay, but what is the last one? What is the last one? The last one tells you that if you have A congruent to B and if you have a natural number, you can raise both sides to that natural number. For example, if I guarantee you that A is congruent to B in some module, say M, and if you want to, you can raise it to power 5, for example, and conclude this one if you want to. Yes? So there is nothing particular for 5. You can raise it to any power, but of course any power is a very big, is a broad term. Yes, I cannot raise to power -1 because a to power -1 in equality, if they are not 0, I can also raise to power -1. That is correct if they are not 0. But a to the power of -1 usually has no place in number theory because it becomes a fraction, and we are not dealing with fractions in number theory. So that is it. So this is why I have chosen n to be a positive integer, not just an integer, because for negative powers there is no guarantee that I have still integers. So there is nothing particular for 5. I can say that any positive integer, so you can conclude. And it's extremely important to realize the other way around is not correct. So this means that you cannot take root from both sides, even though you can do it in inequality. So let us cook up a counterexample here. Can you tell me an example which this one is true, but if you drop the powers and naively conclude this, it might be wrong? And this is a counterexample to show that this is not in general true, so don't trust it. Okay? So can you do it yourself for me? Yeah, let us try some random things to see if it works or not. Yes? Or if you have an idea, I will follow you. For example, let me choose 2 to power 4, which is 16, is congruent to... So let me write 3 to power 4, it's easier. 3 to power 4, 81, and 2 to power 4. Let us just understand that. So this is 81, this is 16. What is the difference? Is how much? Is 65, yes? So can you now give me a number which this one is valid? So for example, do you agree that if I write 5, it's correct? Okay, I was able to cook up this example, yes? So 3 to power 4 is 81. 2 to power 4 is 16. So do you agree that this is a true statement? Why? Because 81 minus 16 becomes 65, and 65 is divisible by 5. So it is a true statement. But let us naively drop the powers, okay? And conclude that 3 without that power is congruent to 2 without the power. Is it a true statement or a false statement? Because 3 minus 2 is 1, and 1 is not divisible by 5. So you see that if I just naively go in this direction, this turns out to be wrong. So be careful. In numbers, in equality sign, of course, if a to the 4 is equal to b to the 4, and then a and b are positive, I can conclude, if I want to, that a is equal to b. But not in the case of congruency. So the operation that we have some limitations for it, you have to have respect for it, is that you are not allowed to take roots in general. Okay? Another one, we cannot divide. Okay? Even if, by the way, even if after division you are not facing fractions. Of course, if you are facing fractions, immediately clear we are not allowed to divide. But sometimes we don't face fractions after division, but still it is not correct. Okay? Can you give me an example? So Yeah, when I'm cleaning, you can think about that. So I'm asking you about giving me a true congruency relation so that you can divide both sides by a number, and after division, still the numbers are integer, but the conclusion is wrong. So this tells you that even if after division the left-hand side remains an integer, the right-hand side remains an integer, but still there is no guarantee that division works. Okay? So these are the differences that you need to appreciate. Do you have any idea? You shouldn't be that picky here. So you just try to, I don't know, random work. So for example, let us write 24 and 9. And then let us cook up a module here. So in which module do you think this will work? So 6, or no, what is that? Or let me make it 8. And let me make it 6. Do you agree with this? Because 24, what is 24 minus 8? Oh, it is 16. So let me make it 6. This is now correct. Do you agree? Yes. Yes, this is correct. Because 24 minus 6 is 18. 18 is divisible by 6. Now, I can divide the left-hand side by 6, and I can divide the right-hand side by 6, and still the left-hand side and the right-hand side remain both integers, yes? If I divide by 6, this becomes what? 4. This becomes 1. If I want to conclude from here, this is a true statement. But if I conclude this, is it true or false? It is a false statement, even though still they are integers. So be careful. Taking roots are not allowed, and dividing is not allowed, yes? Okay, that's it. Now, one thing that I want you to be very good is to simplify things in different modules. Let me see if I can give you an example. Okay. I would say simplify. This is an important example, but again, when I say important, it means that this is something that you need to have in the back of your head when you are just doing this. Simplify. Each number in the given module. And then let me just put this in quotation mark because it's a little bit ambiguous. So number 1, I want you to simplify this. 5 multiplied by 64 to the power of 12 plus 15 times 17. Modulo 7. Or mod 7 if I want to use this symbol. Okay, I want you to simplify this. I will tell you why I say that this is a little bit ambiguous. And of course, needless to say that you are not allowed to use the calculator. It's not hard, for example, if you can use this calculator to calculate it, for example, simply I can put 1200 here. And then it will be out of the reach of your display. Okay, so but still we can solve it. Okay, so I want to solve this following this theorem because I want you to understand more or less every one of these parts that I mentioned there is important to realize. How can I simplify things? But then after that I will tell you how to do it faster. Okay, so if I want to solve the problem, just try to understand this. Okay, don't be picky, so that how should you know this for the beginning? This is your first example. So what I do, this is the thing that you need to pay attention. 7 is my module. Every number that you see appearing in the base, which is above 7, you can simplify it. So I do not choose this one because 5 is relatively simple and it is smaller than my module. Okay? What I do, I would say that 64 is congruent to 7, is congruent to a number modulo 7. But which number? Of course, infinitely many numbers. So here you have to be observant and choose the best one. What do I mean by the best one? Because after that you want to raise this to power 4. To power 12. Okay? 64 to power 12 is a hard number for us to calculate in our brain. Okay? But for example, I don't know, 64 is congruent to 15. Is that a true statement or a false statement? 64 minus 15 is 49, and 49 is divisible by 7. And then I want to use the last part of that theorem because I want to have this combination. I can raise it to power 12, but the price that I have to pay is to raise the right-hand side to power 12 as well. If I ask you, is it a true statement or a false statement? It is a true statement. By the way, it's a really powerful tool in your hand. If I ask you, how do you know that? You didn't calculate 64 to power 12. You didn't calculate 15 to power 12. But what you know is whatever this number is, the subtraction is divisible by 7 in just a matter of seconds. How did you realize that? Because this was not hard to guess. Yes? And then, according to that theorem, I'm just following the rules that I have proven once for all. Yes? So this is already shows the power of a modular arithmetic. Yes? Yes? Yeah, that's what I'm saying. So, but even though this is a good progress, because 64 to power 12 is much bigger than 15 to power 12, but it's still 15 to power 12 is quite big for our brain to calculate. Yes? So this is correct, but not efficient. So the efficient one, when you have especially high powers, is to try to make this number very small. And, of course, ideally, 3 numbers are important for us, which, of course, most of the time, if you are facing a hard problem, it will not work. But at least, you need to look for 3 numbers. 3 numbers that you can raise them to high powers easily. Or might be 4 numbers. So one number is 0, because 0 to any power, more or less, is immediate. And the other number is 1. 1 to any power is immediate. The other one is minus 1 is also very simple because it depends. If you raise to power an even number, it becomes 1. The odd number, it becomes minus 1. The next one I wanted to say, I just correct myself, 10. 10 is of course easy to raise to power, but that's useless again. Because even if you have 10 to power 12, of course I can immediately write it, but that's not useful because I don't know what's going on. Anyway, so the ideal situation are these numbers, but of course they are not always realizable. Yes? But don't just go, especially the questions in the book and in the exam, they have been designed in a way that they are somehow related to those numbers. But this is not a have to, okay? So what I say that, okay, instead of starting from 64 and 15, which was correct, you see 64 is also 1 when it comes to modulo 7. Do you agree with that? 64 minus 1 is 63. 63 is divisible by 7. So that's a true statement. And this is the ideal statement as well. Because now my goal is to raise everything to power 12. When I raise this one to power 12, according to the last part of the theorem, this remains valid if I raise the right-hand side to power 12 as well. Yes? But then everyone instantly knows what is 1 to power 12, which is 1. So what happens? This means that 64 to power 12 is congruent to very, very small number 1 modulo 7. So it means that if you decide to work in module 7, another name for this big number is just 1. Yes, so you can just take it away and put 1 in. But let me just follow this. So this is 1, I would call it number 1. Okay, and then I see that this 15 is also bigger than 7, so let us simplify it. So what can I write for 15 if I am deciding to work with module 7? What do you prefer to write? 1. But by the way, you need to check if this is true or false. So that's correct. And then 17 is what if you decide to work modulo 7? Of course, you can write infinitely many numbers here, as I told you before, but try to choose an optimal one. What do you choose for 17? 3 is good, yes? Because 17 minus 3 is what? Is 14. 14 is divisible. I choose 3. But do you remember one part of this theorem is number 7 up there, which we proved. I have two congruency relations in the same module. That part of the theorem, number 7, allows me to multiply them side by side. Yes? So this implies that. So if you want, let me just write the number. This is number 8 in that theorem. This is based on number 7 in that theorem. I multiply 15 by 17, and this is congruent to I multiply 1 by 3, which is 3. So you see, I am not saying that 15 times 17 is a big number. It's not a big number, but 3 is better. It's much smaller, yes? So when it comes to module 7, there is no difference between this number and 3. Okay? Now, let me put this also in a box. And now let us go back to my question mark. Okay, let me call it number 2. But I want to construct this setup now. Okay? So by the way, I was a little bit careless because this is correct, but this is not, this is what I need is 5 times that. So which part of that theorem I use? I want to multiply both sides by number 5. Which one? So this part, number 5, allows me to do that. So if I use number 5, then it means that 5 times 64 to power 12 is congruent to 5 times 1 modulo 7. So let me call this one number 1. Sorry. So you see, part 8 was used. Part 7 was used. Part 5 here is also used. But still, I want to make this connection, this combination. Can you tell me which part of the theorem I need now to conclude something about the whole combination? What I want to do, I want to have these numbers added together. So I have to add this to this side by side. Which one is that? Am I allowed to do this? Yes, number 4. Yes? So if I have number 1, so 1, I want to add it to number 2 based on part 4. I can do that. So I can write 5 times 64 to the power of 12 plus this number, 15 times 17, and then I will add 5 to 3 modulo 7. Agree? So here I used part 4 of that theorem. But that is exactly my question mark, and 5 plus 3 is a very simple number to calculate. It is much simpler than adding these two numbers. Yes, when it comes to module 7. So this means that 5 times 64 to the power of 12 plus 15 times 17 is congruent to 8 modulo 7. Yeah, this is why I put the simplification here in the quotation mark, because you might say that 8 is good enough. I agree with you, 8 is not a big number, but you can write even better. So what is that number? What is that number? Yes? 1. because 8 minus 1 is 7. 7 is divisible by 7. So I myself prefer to continue and say that this is equal to congruent to 1 as well. So I myself prefer to stop here, but that's also okay. So this is why simplify is a little bit vague argument here. But the convention is this. When I say simplify, not in the quotation mark, I want you to give me a positive number strictly smaller than the module. Okay? So, for example, if you, instead of 8, I can write, I don't know, I can write minus 6. Yes? Because 8 minus 6 is 14. 14 is divisible by 7. So that's also correct. But if I take the quotation mark, the convention is usually this, that give me a non-negative number which is strictly smaller than the module. Yes? So this means that this is positive, but this is bigger than the module. So this tells you that do not stop here, continue, so that you have a non-negative number which is smaller than the module, and you will find only one number with these properties that I told you, because of the division algorithm. So then in that case, everyone will answer 1. Yes, if I put it in the quotation mark, one of you might say 1, one of you might say 8, one of you might say minus 6, all of them are correct. Yes? But when I say simplify without quotation mark, the convention is to write, so the convention, let me just write the convention here. So when you say R, I want you to have this R greater than or equal to 0 and strictly smaller than m. Okay? This is the convention for simplifying things, yes? So in that case, this is the unique answer that everyone should give me that answer. Otherwise, all of them are acceptable. So this is the power of modular arithmetic. So without any calculator, what we understood that this number minus 1, whatever it is divisible by 7. Yes, without doing any calculations, yes? Not direct calculations. But this is very lengthy if you want to do it like this. I did it once because I want you to see that I am using those parts of theorems. Otherwise, it is not possible. But if I want to do it myself, I will do it like this. Not completely different, but I write less. Okay? So what I want to do the same problem faster a little bit. So my goal is to simplify this in modulo 7. What I do, first I go to the numbers sitting in the base and choose the ones which are larger than my module. I have 3 of them here. Okay? And I replace them with the optimized values in that module. That's it. So for example, I do not touch 5. Which number you prefer for 64? First look for the ideal values if possible. What is that one? You can find 1. So just replace that with 1. Yes? And then plus. Instead of 15, what can you write in that module? Just 1. Instead of 17, what can you write? 3. So this is much faster. Yes? So 1 to power 12 is 1 times 5 is 5. This is 3, so this becomes 8. And 8 is 1 again. So if you just write this, that's enough for me. Okay, but I want you to understand the reason that I was able to do it, because I am using many parts of that theorem. At least part 8 is used. You see, part 7 is part 5 is used, and then part 4 is also used. And by the way, part 3 is also used, because I showed that this is congruent to 8. 8 is congruent to 1. I concluded that this is also congruent to 1. So this means that this is part 3 also used here. Okay, is the idea clear? Okay, if that's clear, the second example, I want you to do it, but in the faster way. Don't try to write all the details. Yes. That becomes 0. Yes, it will destroy it. That's better. If this is 14, 14 is 0 in modulo 7. Because 14 minus 0 is 14. So this means that if you see a multiple of your module, just get rid of them because it becomes 0. Yeah, and it becomes 0, that's true. It becomes totally gone. This becomes 0. This is still becomes 3. But then 0 times 3 is 0. But remember, I am not working with exponents. I am just working with the bases. It doesn't mean that I cannot write something for 5. No, you can. For example, instead of 5, if I have chosen to write what? Minus 2, it is working, yes? Because if I have chosen to put minus 2 instead of 5, then I didn't need to do the last part. Yes? Because then it becomes minus 2 times 1 plus 3, and instead of getting 8 and then getting 1, I just directly get 1. That's also possible, yes? But usually, if the number is not that big, I do not change them. But if you change them in this case, even it is better, you changed 5 to minus 2. Yes? I want you to understand that we have different names for integers now, depending on which module you are working. And then you have to practice a little bit to find the optimized value. And it becomes super simple then. Yes? Is that clear? Okay, let me give you another example. And I want to wait for you that you simplify it for me. So 5 to power 15 multiplied by 26 to power 6 plus 1 times 2 times 3 up to times 18. And I want you to simplify it in module 3. So it's a huge number, yes? These numbers are big. You are supposed to multiply. Multiply from 1 to 18. That's also a big number. Add them, and then you want to divide it by 3 to see what's the answer. Okay, so what happened? What's the answer? Ah, was it? You said that it is 0, yes? It might be I wasn't careless. Is it 0? What is the answer? Minus 1 is a good number, but let us follow the convention now. So can you change minus 1 to something according to the convention? Because I have taken this quotation mark away. Minus 1 might be completely right. I will check it out, okay? But instead of minus 1, everyone tells me, what can you write according to the convention? What is another name for minus 1, which satisfied this condition, which is non-negative and is smaller than 3? Because here the module is 3. Instead of minus 1, what is another name? Yes? Plus 2, yes? Because minus 1, minus 2 is minus 3 is divisible. So another name for minus 1 is 2, yes? Okay, let us see. If your answer is correct, then I would prefer to write 2 because of the convention. Okay, let me just repeat again what I'm supposed to do in a faster way. So I will go and check the numbers that are not appearing as exponents. So these are the numbers, and the numbers that are not appearing as exponents are all these 18 numbers. So I have to focus on these numbers, yes? Okay, and then try to replace them, if possible, with the optimized values, which is of course not always possible, but at least for the first problems, think about that. So for example, what can you write instead of 5? You can write a lot of numbers. For example, you can write 2. 5 minus 2 is 3. 3 is divisible by 3. I'm not saying that's bad, but still for our brain it's hard. 2 to power 15 is smaller, of course, than 5 to power 15. But when it comes to hand calculations, it's more or less the same thing. Yes? Minus 1. So the ideal ones, try to think about these 3 numbers first. Yeah, be patient a little bit in the beginning. You might find these ideal numbers. If not, then that's inevitable. Then you have to start with the smallest possible value. But at least for the few example, okay, this one I can write what? Minus, so this will be congruent. Instead of question mark, let me continue with blue. Here, what I do, I just write minus 1. It's preferable to the power of 15. Now tell me, what do you write for 26? Yes? No, 0 is not 26 is not divisible by 3. Yes? Minus 1 again. Even though you can write 2 to the power 6 is not big, but 64 is bigger than the number that I'm supposed to get if I replace it with minus 1. But I want you to understand why minus 1 is correct. You have to be a little bit quick in this, because 26 minus the number that you proposed is what? Is 27. Is 27 divisible by the module? The answer is yes. So I am allowed to replace 26 with minus 1. And then I am not, of course, allowed to change the powers. I have to keep the powers. But what do you think will happen here? There is one number at least I can immediately see that I can replace it with what? 0. I even don't bother about the rest, because that one single number 0 makes everything 0. So what I do, let me just write it if you want to in the future. I would write 1, I do not change 1, multiplied, I do not change 2, multiplied by 0, yes? And then if you want to, I can continue like that until 18, because then I realize that it doesn't matter if I take time to understand them, because whatever they are supposed to be multiplied by this 0. And then I continue. Minus 1 to power 15 is minus 1. Minus 1 to power 6 is positive 1. And then 1 times this is 0. So your answer, Ella, was correct. But according to the convention, so let us use the convention. Of course, if I don't say the convention, you can just stop here. And the answer is minus 1, because minus 1 times 1 plus 0 is minus 1. And minus 1 is relatively really small. Okay? But it's not according to the convention, so I want to continue to write a non-negative number which is guaranteed to be smaller, strictly smaller than my module. And there is only one single number if you want to stick to both conventions, being non-negative and being smaller than the module. There is only one single number that you can find. What is that number in this case? 2. So this huge number that you have here, if you decide to work in modulo 3, is nothing that except 2. Or minus 1, of course. They are all the same. Is that clear? So let me see if I can find another. Okay, so another example show that okay, so we want to show that this huge number is divisible by 7. So the number is actually a nice one, 66 to power 57 plus 57 to power 66. We want to show that this number is definitely divisible by 7. So how can I prove this? Let me just remind you about that remark that I mentioned earlier. So we learned that A is congruent to B modulo M if and only if what happens? A minus B is divisible by M. That was the definition of congruency. Now, if you don't mind, let me change this to 0. Then what will happen? If I change it with 0, you will see why. Then this becomes 0. Yes? And then A minus 0 is, of course, A. So that is important. Whenever you want to prove the visibility relation, one way, of course, is do it as we learned before so far, but it is not that efficient for these kinds of numbers involved. Yes? So, but you know that this is a very important thing. I want you to write it once more. So this divisibility relation can be translated into congruency relation you yourself need to know that the right hand side should be chosen to be 0. Yes? They are equivalent. Instead of showing that A is divisible by M, you can use the techniques that you learned so far for this divisibility, but they are not efficient when it comes to the big numbers. It is preferable to translate this divisibility relation into a congruency relation. How? I told you why. This is the true one. So in this case, you have asked me to show the truth of this statement, but I am allowed to show the truth of which statement? Can you tell me? Instead of showing the truth of this, I can translate this divisibility into the language of congruency. So I would show that what? Can you tell me? This is playing the role of the number A here. And this is playing the role of the number M here. I want to show M divides A. But M divides A can be translated into this new language. So this tells me that I have to show that 66 to power 57 plus 57 to power 66 is congruent to 0 modulo 7. I hope that you agree with me. So if I succeed to show that this statement is true, I am done. Agree? This one I want you to understand. Everyone agrees with me? Yes? Okay. So now the problem is more or less the same problem. In the previous problem, I haven't given you the right hand side. I ask you to simplify it as much as possible. But at least even if the situation is a little bit better, you want to reach to 0 by those kind of arguments we discussed. Okay, so this is your goal. What you do, you start from here. So let us follow the rules that I told you. I want you to help me to do that. So what is the way that you need to think about these kinds of problems? You need to go and look for the bases which are larger than the module. So first of all, find the bases. This is one of the bases, and this is the other one. This is another base, this is another base. So these two numbers, both of them are larger than 7. So this means that let us, for the time being, try simplify these numbers. Always think about the optimal numbers, 0, 1, and -1, but don't push so hard, because if the problem is a little bit harder, it's not a very handy, close to you. So you need to do some work. For example, if one of them is good. They have some ideal relation with 7. Which one is that? Yes? Can be 1. So just do that. Okay, so what I do, I write 7 here. I write 1 for this. Tell me why. Because 57, so I am claiming that 57 has another name which is 1. Is it true? Yes, because 57 minus 1 is 56, and 56 is divisible by 7. So instead of 57, I can simplify it with the ideal situation. But what do you think here? You might be able to find an ideal situation, but I think ideal situations are not working. 0 does not work, because 66 minus 0 is 66, which is not divisible by 7. Do you think 1 works? No. 66 minus 1 is 67. Sorry, 65. 65 is not divisible by 7. Another situation is -1. -1 also doesn't work, yes, because 66 minus -1 is 67, and 67 is not divisible by. So forget about the ideal situation. Okay? So then it means that if there is no ideal situation, you need to find another number, probably the best, the smallest number that you can work with. So what that number is? 3, yes? Yeah. So this becomes 3. But we shouldn't be that happy now. This one we are very happy, because 1 to power 66 has a better name. So let me just continue. But still, I am in a very big trouble. Even though this number is much, much smaller than that number, but for me, it doesn't make any difference that much, because I cannot calculate 3 to power 57 now. Okay, now my goal is to do what? What do you think I will do here? You have to learn to do things gradually. If the ideal situation cannot happen directly, so you have to learn this trick that I want to teach you. Okay? Try, Because you want a have a high power of 57. Try to go to scratch work and try to write some powers of this number as far as your brain permits you, okay? So 3 to power 1 is what? 3. So let me just write equal 3. But remember, you want to be as close as possible to a multiple of 7. Is that right? So here, so multiples of 7 are what? You can just write multiples of 7. I don't know. This list, of course, continues forever. But these are some of them. And then try to write powers of 3 here, some of them. It is 9. I would prefer to go one more. What's the other one? 27. And now you see what happens. Between this power of 3 and that multiple of 7, there is an ideal connection. And the difference is 1. Again, this is not always possible, but these are the things that you need to practice to learn. So it means that I have to put my base of argument on 3 to power 3. Okay? Because that's a good number. So then I will continue like this. Instead of 3 to power 57, I can write 3 to power 3, but I want to have power 57. So what should I write here? 19. Yes? Because 19 times 3 is again 57. Okay? And then I have to copy and paste that one part. So if you don't mind, let me just write this one as well. This is nothing except 21. Yes? It is 27. To the power of 19 instead. Plus 1. But now again, you have the same scenario. This number goes above the module. So again, you can decrease it. Yes? So, but this time it is easy. Which one do you choose for 27 if you're supposed to work in module 7? -1. Okay? So then it becomes what? -1 to power 19 plus 1. Yes? But now this is again simple. -1 to power 19 is what? -1 plus another 1, which becomes 0, 7. Okay, so we got that. So we started from this number, and by doing these kinds of reasoning, I was able to show that this is congruent to 0, module 7. So this means that this is divisible by 7. Yes? Yes, then what you have to do, that's a good question, by the way. This was a coincidence that it was divisible and so nice. But if we have 58, you write the same thing. It gives you how many of them? 57 of them, but you need one more. So then you have to multiply by 3. Okay, then of course you will not end up with 0, but whatever it is, you have to live with it, yes? But that was a good question because, yeah, this was an extreme question that this was divisible by 3. So these kind of, there is no way that I can teach you, but I'm trying to explain things how I think, yes? And if the problem is hard, I myself cannot solve it, or I have to spend a lot of time. So this is the nature of mathematics. But is that understandable? So at least you know what's going on. Yes? Okay. I think I will stop the lesson here now. But how much time do you think we have? 3 minutes, and that is enough because I have already decided about that. So